Alright guys, I think you know the drill here, so I got two quick warm-up problems for you. Make sure you give those a shot. Try them first on your own, and then listen to it and watch the explanation on the video. Alright, so here we go. We're going to go ahead and get started here. Number one says draw a triangle, construct. That means use a compass and a straight edge, the bisector of one angle. So over here, just going to add one step onto our constructions. You just have to draw a triangle. Your triangle can look a little different than mine. It just depends on how you did it. I'm going to call this triangle ABC. And again, your work should look like this. Just pick an angle, doesn't matter which one. We construct the bisector of one angle. So you pick a point, a vertice, put the pointy in there. Remember, you have your convenient arc. You're going to draw your convenient arc across. It doesn't matter how big that is, as long as it's not like super big. And then take your pointy end, put it on one of the intersections of the arc and your side, and draw an arc down the middle of your angle. Then take that pointy end of your compass, put it on the intersection of AC and your original arc. That's your pointy end right here, and draw your arc in the middle of your angle again. Again, your angle when you're done should go from A, or your angle bisector, sorry, should go from A and pass through the intersection of those two arcs. And then I'll use another color so it doesn't blend in here. But then you have your congruent angles right here. That's an angle bisector. Alright, so that's number one. Number two. 2 says JK is perpendicular to ML. So we have JK is perpendicular to ML. So remember, understand how to write this. First, write ML. JK is perpendicular to it. So JK is going to go here. And again, it has a midpoint at K. So it's a perpendicular bisector. Here's K. And I'll just put a J here. Call that a line, I guess. So JK is perpendicular to ML. So bam. Okay. List the congruent segments. So if I'm going to write my congruent segments, you are using your theorems from last chapter, or last lesson. Not last chapter, but that's congruent and that's congruent. So you can say that JM, segment JM, is congruent to segment JL. Okay. And I guess you can say, MK is congruent to, LK. But the main thing here is you're trying to use the perpendicular bisector theorem, right? So those are your congruent segments that you're kind of gleaming from that, because they already kind of gave you that K is a midpoint, so it's kind of given. So those are your congruent segments. All right, so there's your warm-up. That's basically 5-1 review, right? Okay, so here, hopefully you kind of get the idea looking at the title of the lesson. We did in 5-1 just good old, perpendicular bisectors and angle bisectors. 5-2, just going one step farther, just doing bisectors, same types, but now they're inside triangles and seeing what types of relationships these have. So our goal here to be able to prove and apply properties of perpendicular bisectors of a triangle. So we're just adding those into a triangle. And you're going to be able to prove and apply properties of angle bisectors. So in triangles. So it's all about doing what we did in 5-1 and doing them in triangles. Makes sense? Okay. So a couple concepts here, and we'll kind of get into our examples in just a minute. Since the triangle has 3 sides, it's going to have 3 perpendicular bisectors, one for each side. When you construct the perpendicular bisectors, you find that they have an interesting property. And that's, again, if I already went over this with you in class and you've seen it, you know the property. If not, I'll re-describe it here. But the key in class I'm showing you is how to do the constructions. So once you know the constructions, you also just need to know the properties. It's not like you just need to know the construction or you just need to know the properties. You need to know both. You need to know the properties and how to get those properties, how to prove them. But we're proving them through constructions. Okay? Okay. And don't worry about the helpful hand, I'll go over all that. Okay, so this is going to be that first property that we went over. when we do the constructions, and they have the important property, the interesting property it has. It's going to have what's called a concurrency point. So if I constructed the three perpendicular bisectors of a triangle, they're all going to intersect at the same point. So when three or more lines intersect at one point, that point is not called an intersection point anymore. It's called a concurrency point. So that's what they mean when we say a concurrency point. Now, when you draw these, hopefully you can kind of see when I do the construction. Obviously, it looks a lot crazier because we have this whole segment drawn and this whole segment drawn. They're just drawn, making a neat picture of it, and that whole segment drawn. So when we're doing construction, you'll see a big old, three big old lines, and they all touch at the same point. If you did clean that picture up, this is what it's going to look like. Okay, you're going to have point P right here, and this is your concurrency point. And again, these little red segments right here, those are your perpendicular bisectors. We just kind of cleaned it up a little bit. It doesn't keep going because that way it kind of blends in with all your other line segments, right? So what you need to be able to then glean from this is understand that when we did this construction, we're able to construct a circumscribed circle using point P as the center. So the property that comes from this is that PA, PB, and PC, those are all the radius of the circle. So that's why these three distances are all equidistant, because they all represent the radius. But again, in order for you to be able to state that, you need to be able to show that P is formed by finding the concurrency point of three perpendicular bisectors. So all this information is going to need to be given to you before you can make this statement. You need to show, so I'm looking at point P, I need to show that that's a perpendicular bisector. So it's got the perpendicular, the right angle, and the two congruent segments. You need to be able to show that this is a perpendicular bisector with the right angle and the congruent segments. And you have to be able to show that this third segment is a perpendicular bisector because it breaks it into two congruent segments and has a right angle. All that has to be given. If any of that's missing, you can't then state that these three segments, that from the concurrency point to each vertex is congruent. So it all has to be there. So you need a lot of information, in other words, to make this conclusion. Okay. So again, that's an important. It looks kind of complicated. It's really not so bad. It's just it's three things that you have to do, but it's the same three things you have to be able to show. So it's easier to learn that way. And when you are describing circumcenters, this stuff I went over in class, hopefully, because I haven't done it yet when I'm doing this video, but hopefully I went over this. The circumcenter can be in three different places. It can be inside a triangle, outside a triangle, or on a triangle. So when you're constructing circumcenters, the picture that I had, P's on the inside, but it's not always on the inside. You're going to need to understand the difference between those. So the three types, you got your acute triangle, and if it's acute, then when you do your circumcenter, you kind of have your, bam, this point, I kind of got this point, and I'll do this point. Okay, this point P is going to be on the inside if it's an acute triangle. So your circumcenter would be on the inside for an acute triangle. If you're doing a right triangle, then you need to understand when I'm doing my three points, the one that really matters when you're doing this is understand, obviously when I do my perpendicular bisector of the hypotenuse, it's going to go through the hypotenuse, right? Well, the next one, it's going to go through the midpoint here, and it's going to actually intersect that first perpendicular bisector at the hypotenuse. And the third one's going to do the same thing. They're all going to intersect on the triangle. So this will be on the hypotenuse. Let me be more specific. So if you have a right triangle, your circumcenter is always going to be on the actual hypotenuse of your triangle. And then if you kind of see the trend here, as my angles are getting bigger, looks like my circumcenter is moving its way outside the triangle. Well, that's what's happening. If you have an obtuse triangle, so I'll do an obtuse one. So in this triangle, you have your perpendicular bisector. Perpendicular, cuts in half. You do a second one, and I'll do it, and I gotta go up here, that's where they're gonna touch. If you do this, the longest side here, I'm gonna cut that in half. I do that perpendicular bisector. Notice where they're intersecting. And then you do your third one. Again, what's going to happen is that concurrency point is now outside of the triangle. So outside. So these are the three types. You need to know that. So I hope you wrote those down. Actually, they already had a picture. I deleted the picture because I want to draw it and show you. I want you to draw it as well. Okay. So that's what you need to know about circumcenters. Like, what is a circumcenter? How is it found? Well, it's found by finding the concurrency point of the three perpendicular bisectors of a triangle. But you also need to know where those concurrency points can be located. And it can be inside on the hypotenuse or outside the triangle. So you need to understand all these properties. And it can, those properties can add up pretty quick. You might think, oh yeah, I got this, but it's easy to kind of get them confused once we start doing our other concurrency points. So let's keep them straight. Okay. So again, we already talked about the circumscribed circle, so I don't need to go over that again. But that's, again, why we have our three congruent segments, right? These are all the radius of the circle. Bam, bam, bam. All right, so using that concept here, let's find GM. So GM, it looks like they're giving us is this segment right here. So we need to look and see, and it's easy, when we only have one type of bisector we've covered so far. So you might already kind of have an idea of what we're dealing with, but let's say we didn't know which type of concurrency point we're dealing with. Well, here's going to be your clue to this problem. 19.9, 9.5, these are all segment lengths, and we need to find, again, GM. So I'm going through this. 19.9 looks like it's this segment right here. Okay, I know that 9.5 is this segment right here. And 18.6 is going to represent KH, which is only half. So they're all three different segments, including, MJ. Now I realized too, when I was, I said I deleted some things. I actually did delete an important statement down here, but I'm not gonna, since I have the opportunity to change that statement, I'm gonna do that now. So let's add some things to this to help us solve this problem. Now, by the way, what the statement that I deleted was a statement that said that MZ is the perpendicular bisector of GHJ. So anyway, let's just say we had this instead. Let's say they told us that that segment was 19.9, and they told us that this segment was 19.9. And because they gave us this segment was 19.9, it looks like I should be able to draw a circle, what would be called a circumscribed circle, around that triangle. Well, if I can do that, because again, let's assume they gave us this. Again, the other statement I deleted, they were telling me I had perpendicular bisectors. This one's a little bit more creative. This one, they're giving me the three congruent segments, which means this must be my circumcenter, which means that these must be perpendicular bisectors. Therefore, these segments are being cut in half, which means, go one step farther, that must be 14.5. That's going to be your GM. Again, you know that because that other segment was 14.5. So once we understand we have perpendicular bisectors, then I know that that segment got cut in half. Okay, again, I just deleted a statement there to help us find that, so I had to add some information then to fix it. Alright, next up, again, we're going to do the same basic thing. Now this one I'll have to add things. I deleted this one, I think all of them. But it says use a diagram, find GK. So let's just say we're dealing with the same problem, okay? So we still have our 19.9s here, and our 19.9 here. Okay, so in this situation, since I know that I'm dealing with perpendicular bisectors, that means that's a right angle, and I'm going to call that A. The reason I'm calling that A, I have a right triangle right here. Look at KHZ. I'm going to draw the triangle right over here. Okay, the little side I'm going to call A. I have this side right here, which is my other leg, which is 18.6. This is going to be my 19.9. So in this situation, I'm able to do Pythagorean theorem and solve for A, just because I know that's a right angle. So in this case, what you'll do is you're just going to set up A squared plus B squared equals C squared. So solve this, we're going to go A squared plus 18.6 squared equals 19.9 squared. So 19.9 squared is going to be 396.01. 18.6 squared, that's going to be 345.96, and I'm going to solve from there. So I'm going to start by subtracting my 345.96 on both sides. So those obviously cancel. You get A squared equals, and here we go, 396.01 minus 345.96. So I get about 50.05. Now one thing I noticed when I was grading is, I was grading your homework, I had a lot of people that had like x squared equals 9. That was one of the problems I was grading, and they were saying x equals 9, which, well, that's kind of what I was thinking, like what the heck. Remember, when you have a square, you need to get rid of it, like I have here. We need to do the opposite of squaring. The opposite of squaring a number is square rooting it. You should know this by now, okay? So this would be x equals, technically it's plus or minus 3. If we're dealing with a distance, obviously it's going to be a positive number. So that's what I'm going to do here. I'm square rooting both sides. So we need to take the square root of 50.5. So if you do that, in this case, I'm going to get 7.07. Actually, I don't want to say equals because it's not equals, it's approximate. I had to round that off. And that's going to be GK. GK is approximately 7.07. So you don't have an exact number. I mean, if you wanted to keep it exact, you'd have to keep it as the square root of 50.05. Keep that approximate there. Okay. There's a couple things you can do with circumcenters. You can do Pythagorean theorem on them because you will have a bunch of right triangles inside this triangle. Use that to your advantage. Alright, and keep on going here. We're going to find JZ now. Same information. JZ. So JZ. Now let's just say, again, I was given. This is where you'd be given that. Let's go MZ, KZ, and HZ. And actually, they were looking for what, JZ, and I said that backwards. Okay, so I got MZ, KZ, and ZL. Sorry, you can say LZ and LZ are perpendicular bisectors. So again, if I was given this figure and I was given this statement, you have to be given that statement, okay? Otherwise, you don't really know the answer to this. Then I know that these are all congruent. That's kind of what you'll be able to glean from that. So in this case, JZ would just be 19.9. Nothing to solve for there. Just know the theorem about the circumcenter. Okay. All right, moving on. So here, now we have to find the circumcenter of triangle GOH with these vertices. Now, you should know the drill by now. If they're describing a figure, especially if it's on the XY plane, we need to draw it. So I'm going to pause the video real quick and draw this, and then we should easily be able to tell what we need to do in this problem. Should be pretty clear. Alright, so here's our triangle. Looks like, yeah, if you draw it, you should notice we have a right triangle. Now, if you remember from, find the slide here again, if we have a right triangle, understand that your circumcenter, which we're looking for, is going to lie on the hypotenuse. But what point on the hypotenuse is it? Well, that's where your perpendicular bisector lies. So that would be the midpoint of the hypotenuse. So our goal is we get, let's see, there we go. Our goal in this problem is just to know that, and we just need to find the midpoint. I'm just looking for the midpoint of GH. That's all we need to do, but we need to understand that's where the circumcenter is located on a right triangle. So I know that H is at 8, 0, and G is at 0, -9. I'm going to find the midpoint. I'll call this point C for circumcenter, and C is going to be the average of the x's, so 0 plus 8 over 2, the average of the y's, so -9 plus 0 over 2, so 8 over 2, -9 over 2. Point C is going to be at 4, -4.5. Again, your goal here is to make sure you have that connection, you understand the circumcenter of a right triangle is the midpoint of the hypotenuse. So when they're asking you for the circumcenter of that triangle, they're asking you for the midpoint of the hypotenuse. That's all you gotta know. As long as you know the midpoint formula, then you can apply the midpoint formula to the problem. And again, you understood what they're actually saying, so you end up just doing basic midpoint. Okay? So that's circumcenters for you. It's a lot of information there that you can kind of glean from one theorem. And then there's more on top of that. So again, it's important that we kind of understand and remember these connections. Again, in class I'll try to put these all up at once so you can kind of compare them, because you do want to have these all in one spot, like all the theorems and the properties, so you can start to study them so you don't get them confused. Tends to be a problem, I think, on some of the lessons we've done. Anytime I do multiple theorems at once, you get lost. It's because you're not studying it. Make sure you're studying these. Get them straight, because now we're moving on to another concurrency point called the incenter. So the incenter of a triangle is equidistant from the sides. That's a property, but again, how do we find the incenter? Well, the incenter is formed by the angle bisectors. You'll see my angle bisectors here. If you know the angle bisectors, they're going to touch at a concurrency point here, and what's formed is what I did in class hopefully already. If not, I will be, is an inscribed circle, which means it's inside the triangle. Well, if the circle is inscribed, or it's inside the triangle, remember the properties of circumcenters is that they can be, the circumcenter can be inside on or outside of a triangle, not the incenter. Think incenter, inside. That's an easy way to remember that. Okay, the incenter will always be inside your triangle, okay? And again, the distances that we're showing congruent are these three right here. And this goes from your angle bisector theorem. If you remember, we had our angle bisector theorem. If I had an angle bisector, these distances are equal, right? And the reason why you're always given right angles here, it's a bad scale, but you can see how that's kind of how it's formed in your triangle, is you're going to form right angles to your circle. And if I took, say, PC as my angle bisector, notice these are going to be congruent by the angle bisector theorem. Or if I did AP, I know that YP and XP are congruent by the angle bisector theorem. So we're just using that angle bisector theorem to help prove the incenter theorem. Alright, again, just a little remember, you can read that if you want. We'll be applying it. Unlike the circumcenter, again, the incenter is always inside the triangle, so even I'll show you an example with an obtuse triangle. Again, if I have an obtuse, normally with the circumcenter, you remember that the concurrency point would be outside the triangle, but here I'm doing angle bisectors. So here, all my angle bisectors, again, bisect, bisect, got two arcs, and then I could do the same thing over here. And they're always, no matter what, those points are always going to touch inside the triangle. Okay, remember, inside, in center, in the center. And again, this is that inscribed circle. As I was saying, from here you can draw the radius to that circle. And again, when you draw the radius, it's going to form a right angle with the side of your triangle. Because that's the radius of the circle, those distances are going to be the same. That's how we prove it through constructions. Alright, so on these, again, just real quick questions, again, understanding the applications of these. QX and RX, in this case QX and RX, are angle bisectors. They don't have the angle bisector labeled there, but you know it's there. Here, we know that's congruent. Find the distance from X to PQ. So X to PQ. So I want this distance right here. Well, because they gave me this is 19.2, remember these are equal, right? So I just found it. So that's going to be 19.2. See, some of these, you know the properties, you know the answer. No work to do there, right? That's a tick mark, by the way. It's an ugly one. Okay. That was fast, right? Know the properties. And again, that's really a lot of these. If you just learn these theorems and all the different properties, a lot of these questions are just plug and chug. You just need to know your theorems. Next up, QX and RX are angle bisectors, so it's same figure basically. QX, I'll use different arcs on this, but there we go. I need to stagger those arcs a little bit. There. Okay, so QX and RX are angle bisectors. Find the measure of PQX. So now I got PQX. So I'm looking for this angle right here. Well, they're giving me this angle, which is 52 degrees. So what I'm going to do, and they gave me this angle, which is 12. So understand that's 12 as well. Now, in this problem, what we need to understand is that in order to solve this problem, I need to find this angle right here, the whole thing. If I can find the whole thing, then I know that these angles are being bisected, so I just got to cut it in half. Well, now to find that angle, let's expand out to this triangle. I know the other two angles in that triangle, so if I know those two angles, then I can find angle Q. So this first step is to find angle Q. Bam. So here are your three angles. I'm going to go 180, and I'm going to subtract my 52, and I'm going to subtract my 12 and my 12, which is 24. Again, I know the three angles add up to 180. Now you can tell this one should be a little obtuse. So if if it's drawn to scale, we should be able to get that. But 52 plus 24, so 52, 62, 72, 76. So I have 180 minus 76, and that's these two angles combined, R and P. So you subtract those, you're going to get 104 degrees. Now that is the measure of angle Q. I don't want the measure of angle Q. I want the measure of angle PQX, which I know is being bisected. So I'm going to take over here the measure of angle PQX equals 104 divided by 2. Cut it in half. That's what bisect means anyway, right? So that would be 50, and again we have 4 divided by 2 is 52. 52 degrees. That's again about as crazy as those could possibly get when you're dealing with angle bisectors. Alright, last one. We got just basically a application problem here. So again, we have a city. The plans to build a firefighters monument in the park between 3 streets. We got these 3 streets. Picture's already drawn here. We're going to draw a sketch to show where the city should place a monument so that it is the same distance from all 3 streets. So I'm going to draw a monument here, and this is what we're looking for. I want that distance that distance, I didn't draw this in the right spot, and that distance to all be the same. Obviously it's not the way I drew it. I can show you how to find it though. Justify your sketch. So here's how you justify it. We're going to draw. So all you have to do is kind of say the fire station, firefighter's monument. Needs to be located at in this case, we'd be doing 3 angle bisectors. Remember, that would give me this segment, and that segment, all congruent. So it needs to be located at the incenter of the triangle formed by the 3 streets. Bam. Okay, so and I got my sketch. I'm justifying the sketch, and again, you can even draw your little circle if you want to. You don't need to. That's an ugly one. I had a hard time with these. If I can't construct them, I look a lot better in class when I draw them using a compass or on paper, but I can't do that here. So anyway, that's 5.2. I'm talking about circumcenters and incenters. As you get into 5.3, which is talking about more concurrency points, so there's more to learn. So make sure you're learning these as you go. And hopefully, I went over some of these in class already. So again, we got our lesson quiz, real quick one, 1 through 3. Once you do the lesson quiz, do your reflection, and I'll see you guys in class.